I'll stay on this side.
Yes.
This.
Sure.
Down here. People behind me want to move elsewhere, so that because we'll be standing. So you can go on this side or come inside. If anyone needs that space, you can take
Yes,
this.
sir, I can.
We'll wait for a minute and then start. Okay, so let me begin. I'll sort of take off from where we stopped the last time. So this is the slide that I was showing you, and I was talking about dwarf galaxies. But before I start, if there are any questions from either the Zoom audience or from people here, based on what I said in the previous lecture, you can ask now. Yes.
Sir, in the elliptical galaxies, you have said that the light profile of these galaxies are very smooth. So I don't understand this.
Okay. So, look at the light profile over here. It is not radially smooth, correct? Would you agree with that? In the sense that if I start from the center and I go radially outwards in any direction, the amount of light that is there keeps on going up and down. Because as you encounter the spiral arm, it becomes brighter, and in the interarm region, it is fainter. Correct? So this is what I mean by this being non-zero. Now contrast this with the picture of the elliptical galaxy. Okay. So there is a twofold symmetry to it. If you rotate it by 180 degrees, the elliptical galaxy will look identical identical to what it is right now. So it has what is called a twofold circuit. It is very smooth because if you go around along any direction, the light intensity only goes down. It does not go up and down like it does for a spiral. That's what I meant by smooth. Any other question? So if there are any questions from the online audience, you can ask now, or we can of course take questions at the end. I don't see any messages in the chat, and I don't see anyone speaking up. So yeah, there's a question.
Is this missing satellite problem?
Yes.
From a simulation point of view. So this I want from a simulation point of view, whenever halos are considered, that is, so we don't know like how what's the like exactly how the dark matter is distribution. So like, is it viable to like for solving this or like, just understanding this missing satellite problem to consider smaller some sub dark matter halos?
Yes. See, the missing satellite problem is not clear to me. It's a problem at all. In the sense that in cosmological simulations, you do form lots of low mass halos. Okay, that is correct. But remember, those cosmological simulations are fine-tuned. We will come to that. Why those simulations themselves may have to be redone. So I would like to visit this problem from the observational side, where either we don't see these galaxies because they don't exist, or B, we don't see them because they're very faint. And either of these possibilities could exist even without changing the dark matter paradigm. But I think even the dark matter paradigm may get revised. So I think it's people have been panicking about the missing satellite problem for a long time, but I don't think it's that serious at all. Anyway, we'll come to that. Okay. So okay, so this is what a typical dwarf, or I should say a very special kind of dwarf galaxy looks like. It's called 1ZT18. The stars that you see here are the first stars that are forming in this galaxy. And how do we know that? How would you know that these are the first stars forming in a galaxy? Huh? How would you tell whether this gas that you see in this galaxy it has formed stars previously or not? Yes, that's absolutely right. From that corner, metallicity you can measure. Okay, if you measure the gas phase metallicity, that is very, very low. That indicates that the gas has never been polluted with metals, which means there hasn't been any previous generation of stars born in that galaxy. So this galaxy is like that, very pristine. The gas is like virtually hydrogen and helium gas. Very, very pristine gas. And this is a very low mass galaxy. So this in galaxy formation we call cosmic downsizing. Okay? Which means that the most massive galaxies that we see today form their stars the earliest. Okay? So if you take the mean age of the stars in a galaxy as a parameter, then the most massive elliptical galaxies sitting at the centers of clusters are those stars at the oldest ages. And at the opposite end, the vigorously star forming dwarf irregulars like 1CP18 have the youngest ages. And they're very low mass. Opposite end. 10 raised to 8 to 10 raised to 12 solar masses, we said. This is like 10 raised to 8, and those guys are like 10 raised to 12. Okay. So if you go to higher redshifts and ask the question, we've done all this morphology business. Do you see galaxies with the same kind of elliptical, lenticular, etc., at redshift 1. So these are a sample of galaxies at redshift 1, and you can already see that there is a problem. Okay, you can't really make out all your familiar spirals and ellipticals and so on. Some of them could be called ellipticals. The one at top row, middle one, maybe that's an elliptical. And maybe top row, sorry, middle row, middle column, bottom most row, maybe that's like a spiral. But it's not very clear. If you go to redshift 3, then the situation becomes worse. You see these objects. Okay? So then names like tadpole galaxies and things like that begin to emerge. But basically, you don't see any real, well-defined shape. And these are at redshift 3. But there is a problem here, which is we are not seeing the rest frame optical for these galaxies because the observed wavelength is 1 plus z times the emitted wavelength. Suppose something is emitting at 5000 angstroms, but it's at redshift 1. You will observe it at 10,000 angstroms. So you won't even see it in the optical. It will be out of the optical. On the other hand, what you will see in the optical with a telescope like HST will be the rest frame ultraviolet. And we know that the rest frame ultraviolet is the morphology looks very different from the rest frame. So what do? You need to obtain rest frame optical images for these objects to do a one-to-one comparison of the morphology. And this is something that has only become possible technologically in the last 1.5 years. And that is because the James Webb Space Telescope is now available. So what you see here, the top panel is the galaxy as seen with the Hubble Space Telescope. And in the bottom panel, you see the galaxy as seen by the James Webb Space Telescope. Same galaxy, okay? Except that now you are seeing it in the rest frame optical. And now suddenly for the first time, you begin to say, okay, yeah, and these are all at redshifts between 1 and 3. So they're all high redshift galaxies. Oh, that's a spiral galaxy. But if you had looked at the same object with HST, you would have seen a green blob like that. And you would have said, I don't know what it is. This is the power of JWST because for the first time it offers you comparable resolution to HST, better sensitivity because it's a bigger telescope, and for the first time access to the rest frame optical at these sensitivities and resolutions. Okay, there were other infrared telescopes before this, like Spitzer Space Telescope. But if you compare the sensitivity and resolution of Spitzer with JWST, JWST is like 100 or 1000 times better. And that's what enables. So we can now redo galaxy formation. And now what is beginning to emerge already from the early JWST studies. The first study was published in last August. So it's less than a year. In the last 9 months, it became quite clear that what we were thinking about when galaxies form, okay, how rapidly they form, and when did the first morphological structures emerge, all these things have to be revised. So the first galaxies now we believe formed much earlier than 400 million years, which is the number I quoted the last time, probably 200 million years, right? So they formed early. Then very massive galaxies also formed very early. So not only did the process of galaxy formation start early, but the growth of stellar mass in galaxies also happened much more rapidly than the current models. Ready? And the third thing is these kind of morphologies, spiral galaxies, other kinds of these galaxies, were in place much earlier than we had thought. So this is the reason I said you don't worry too much about the missing satellite problem, because I mean this whole thing, all the simulations may have to be redone. Will have to be redone. And this is not totally shocking or completely wrong, because what the simulations do is that they have some free parameters, some knobs that they can turn. And they turn those knobs so that the simulations match the observations. So now the observations have changed because of JWS. So the simulations have to be redone by turning the knobs again and trying to match the observations of JWS. Okay, so this factor is very important. That's the thing why JWST is very, very useful for studies of distant galaxies. So galaxies, most of the galaxies don't live in isolated by themselves. In fact, the majority of galaxies live in groups. So what is a group? Group is something where you have maybe 2, 3, 4 big galaxies and maybe 30, 40, 50 small galaxies. Right? Small galaxies and the dwarf galaxies. So we live in a local group. We have 3 big galaxies. There's the Milky Way, there's the Triangulum galaxy, and there is Andromeda, which is the most massive. The Milky Way and Andromeda are quite massive, and Triangulum is much less massive, but nevertheless much more massive than the dwarfs. So we have 3 sort of regular galaxies colored in yellow, and you have a bunch of dwarf galaxies. Observing the galaxy, or any galaxy for that matter, in different wave bands gives us different kinds of insights. So if you observe in the radio continuum, you see mostly synchrotron emission from accelerated charged particles moving in a magnetic field. So that's what you see in the radio. In atomic hydrogen, when you use the H1 emission line to map the distribution of neutral hydrogen in the galaxy, you can trace not just the amount of neutral hydrogen, but also you can measure the Doppler shift of the gas clouds. And using that, you can measure how the galaxy is rotating, or at least how the neutral gas is. Molecular hydrogen can be measured, not directly, but using proxies like carbon monoxide. And these rotational transitions give you the distribution of molecular gas in the galaxy. And this, as I said already last time, the distribution of molecular gas is important because it's the region where stars are going. With infrared, you are able to probe the distribution of the dust. So what infrared does, what dust does is that it absorbs the photons that fall upon it, gets heated, and then re-emits. So in the universe, you have 2 kinds of black bodies: the dust black bodies and the stellar black bodies. The dust black body can be very quite hot, therefore it can emit, say, in the mid-infrared or even in the near-infrared, or it can be quite cold, where it will emit in the far infrared. In the near-infrared, we can trace the distribution of the low-mass stars in the galaxy. And we know that low-mass stars are much more common than high-mass stars, and therefore their distribution actually tells you the overall distribution of stars in the galaxy. In the optical, you see the stars, of course, quite clearly, but you also see the dust in absorption, because dust is very good at absorbing and scattering optical light. When you go to the X-rays, you see supernova remnants. You also see lots of individual small sources, which we call X-ray binaries. We'll come to that. And if you look at in the gamma ray, then it's a mixed bag actually. There are gamma rays which are coming from extremely hot regions of star formation. There could be gamma rays coming from some of the most massive stars. Okay? and so on. Right. The next structure that you encounter, in fact, the largest structure that you see, is the galaxy cluster. And if you ask the question, how does morphology change as a function of distance from the center, there's a very clear trend. So close to the center, you will usually have one big, massive, luminous, elliptical galaxy. And as you go further from the center of the galaxy, that defines for you the center, because that's the massive object which has fallen to the center of the potential well of the cluster. And as you go radially outwards, you find that the morphology is initially mostly elliptical, then it changes to mostly lenticulars. And if you go to the outskirts of the cluster, because you can't see it very well here, but if you go to the outskirts of the cluster, you encounter more and more spiral galaxies. So spiral galaxies are common in groups and in the field and on the outskirts of clusters. But if you go into the inner part of a cluster, you will have only ellipticals and lenticulars. The H1 line. So this is a very, very powerful tool for studying gas in galaxies, because this particular configuration of the hydrogen atom, where the proton and electron spins are aligned, has a slightly higher energy than their opposite. So if an atom transitions from aligned spin to opposite spins, then a photon is emitted. And what is the wavelength of that photon? Approximately 21 centimeters. So that's why it's called 21 centimeter radiation. Right? It occurs at about 1420 megahertz in the radio band. And this, along with, of course, optical studies as well, were responsible for pointing to the existence of dark matter in galaxies. So if you just took the galaxy as a whole, whatever you see is all there is. If you assume that, then the velocity of gas as a function of radius should have gone up and then gone down. Okay. Over here, at large distances, that fall off in velocity will be Keplerian. Okay, which means it will be 1 over root r kind of fall off here. But what was actually seen was that here it went up as expected, but then it began to deviate quite early. And as you went further and further out, the measured velocity curve, rotation curve of galaxies, particularly galaxies that rotate quite a lot, rotate at high speed like spiral galaxies, was flat. Okay? And the explanation that was offered very early was that this is due to the presence of some matter. Yes.
Why does it not deviate at the start also?
It actually does deviate. This is a logarithmic okay. Yeah. So it does deviate. Remember, this is a linear scale. Okay. So what happens is the dark matter has a different radial profile than the visible matter. So it's because of this, near the center, there isn't too much dark matter. There isn't too much difference between the visible matter and the dark matter. And as you go outwards, the amount of visible matter falls off very rapidly, but the amount of dark matter does not. Okay? And remember, I mean, if any object that is within the radius will not contribute to the potential and therefore to the so here's a very interesting observation of two colliding clusters. Okay, So this is called as the bullet cluster. Okay? And what you see here is the shock wave of the gas. So the pink color is the X-ray gas. The optical is shown in this yellow color, the galaxies, etc. And the dark matter is shown in. So the dark matter seems to coincide with the positions of the galaxies. Okay, you would say, okay, that's fine because galaxies are massive objects, but not in clusters. In clusters, most of the mass, majority of the mass is not sitting inside the galaxies, but it is sitting in the hot intracluster gas. So this indicates that there is actually a shift between the center of mass of the baryonic matter and the center of mass of the total matter. There is an offset. And this theory, I mean, this observation has played an important role in lowering the possibility of there being other explanation than that. So the other way of explaining this rotation curve is to say that who told you Newton's law applies on all scales. Okay, maybe it's not 1 over r square. Maybe it changes as a function of this. So there is a family of want to ask something? Yeah.
When you go to the previous slide,
yeah,
you said that because we do not see much deviation from the calculated. So, but the only way to detect dark matter is through rotation curves, right? So we are assuming basically that there is less dark matter.
No, what we are doing is, we are not assuming that. What we are doing is, this is the rotation curve. Tell me what is the matter distribution which will reproduce this curve. Okay, so we are not saying that there has to be less dark matter. If it comes out that way, that's what we believe. It has to fit the data. So we are not, this is a purely, that measured curve is a pure real laboratory experiment. I mean, not laboratory. Sky is the laboratory, but yeah.
So,
yeah.
What is the calculated curve over there? How is it calculated?
How is it calculated? See, what you can do is, suppose you assume this is the galaxy. You can measure what is the stellar density as a function of radius. So you know the mass profile of the galaxy. Then you can calculate, suppose there's a test particle. Suppose there's a particle of gas which is sitting, say, at this radius. How much acceleration will it feel? As you go further out, the acceleration that you see becomes Keplerian, because then you can make the simplifying assumption that all of this mass is sort of concentrated at one point, like it is for the sun. Much of the mass of the solar system is in the sun. So you can do that. That's how you can predict or calculate the expected rotation curve, assuming there's no dark.
I don't completely get why there's some sort of maximum. I thought it would be like a completely falling off sort of profile.
No, that's because the matter is not centrally dominant. It's not as if all the mass is sitting at the center of the galaxy. Galaxy is a very big object, right? So that kind of Keplerian fall off doesn't happen till you are outside the galaxy. Yeah. Yeah.
Also, in this picture, how do we know that the dark matter is present in that region? Is it detected by the lensing?
Yes. So I'll come to that. Mergers can alter morphology. This is an important point that you should remember. So these are tidal distortions from interactions. Again, Hubble Space Telescope. So galaxies are in the process of transformation. This generally happens from disks to ellipticals, And in late stages of a merger, the two galaxies are no longer distinguished. And what will the merger product be? So, this is a simulation of a collision between Milky Way and Andromeda, which is going to happen in the future. What you see here at bottom right is the number of years after today. Okay, so this is every second here, like last time, every second is 100 million years. Okay. So the Milky Way rotates around itself about once every 200 million years. So every 2 seconds it's going to go around. That's what is happening. That's your central bar that is there, and the Milky Way is spiral which is rotating. Now we sort of zoom out, and we see the Andromeda galaxy coming towards the Milky Way. The Triangulum galaxy, which is the third massive galaxy, does not actually participate in the collision, but does a flyby so that it contributes to the gravitational potential, but doesn't actually collide. So here's your first collision going through the three-dimensional structure. So that Triangulum galaxy is somewhere in the background. And now there's the second pass, third pass, fourth pass, fifth pass, etc. And now Triangulum survives, but Milky Way and Andromeda are gone. And what is what does this thing remind you of? Elliptical galaxies, right? So the light profile will be like an elliptical. The stellar population, so there will be some amount of vigorous star formation when the two things collide, but those stars will rapidly die out in massive ones. Yeah.
So where are you observing this event from?
From space. This is a simulation.
From the local galaxy.
A little bit distance so that you can see both of them colliding. This is just a simulation from Wikipedia, so you can just look for Wikipedia, and there's a whole article about this. And so about 7 billion years from today, we'll also be gone, because by that time the sun will swallow the earth. But then the sun will be a white dwarf, and will be gone, and also the Milky Way will be gone. A lot of tiny streamers could get created. So it is possible that the sun, which is a white dwarf, would get thrown out of the galaxy, also out of the merged pair. So, right. So this is as just to illustrate the fact that galaxies can collide. So now I'll talk about a little bit about gravitational lensing, because that is also quite important nowadays. But I won't say too much, because I think there will be some of the other lectures which will cover that. But I'll talk about lensing from the perspective of large-scale structure and galaxies. So the first lens was discovered in 1979. If you ask the question, why was it not discovered sooner? The clue lies in this over here. This is only 1 arc second. So only when you had telescopes with the kind of performance needed so that you could resolve structures on a scale smaller than 1 arc second, did it become possible to find the first lenses. So here's the lens, which is the galaxy, and 1, 2, 3, 4 are 4 images of a background quasar. Okay? So there's a point source behind the galaxy. It's got a lens and multiple images. So can galaxies lens only quasars, or can they lens other galaxies? Certainly they can lens other galaxies, no problem. So these are Einstein ring gravitational lenses. Einstein rings are formed when there is a very almost exact symmetry, the problem, where the lens is exactly in line with the background object, and you see these kind of lenses. So the bluer structures that you see, that is the lens galaxy in the background, and the sort of yellowish structure that you see, that is the lensing galaxy. So for purely geometrical reasons, it is easier to find these kind of lenses than vice versa, which means this is clearly a star-forming galaxy being lensed by a elliptical type passive galaxy. Okay? Those are much more common than the universe. Can clusters also lens? Yes, of course. So if you have a cluster of galaxies, along, of course, with its dark matter, then the galaxy, there's a blue galaxy in the background, it comes forward, it gets lensed, and multiple lensed arclets or arcs are formed in the image when you observe the galaxy cluster. So this is an example. So that's an arc, that's an arc, that's an arc. This is an arc. Second arc. And it's possible to actually now identify each of these arcs and build mass models for the galaxy cluster. So the main advantage of gravitational lensing is that it is sensitive to all kinds of matter. Dark matter plus baryonic matter in any form, molecular gas, atomic gas, we don't know. And also bending of light in GR is wavelength independent. There's no lambda term in the equations. So it can be observed, provided you have sufficient angular resolution, it can be observed all the way from optical theory. And then you can build a mass model for this. So it's basically like the lens, like your lens that you have, except that the distribution is different. So the sort of effective refractive index changes from location to location. So this is a mass model of the cluster. And now with JWST, you have so much improved sensitivity that you're finding lots and lots of arcs. So what is shown here, let's look at 7A, 7B, and 7C. That's essentially 3 images of the exact same object. And you can see that in each of those images, there are sort of 2 peaks. In 7A, 7B, 7C, there are 2 distinct peaks. This seems to indicate that this may be a pair of very galaxies that is about to merge or is merging. Right? And that's why there are 2 peaks corresponding to each of those galaxies. But now each of these numbers, like 2A, 2B, 2C, is supposed to be the same object. 3A, 3B, 3C will be the same object, and so on. And it goes all the way to 15, 16, and so on. Right? I think 16 is the largest object. So in one single image, we are able to find many lenses. And therefore, we will be able to build a very, very accurate mass map of the cluster. Since these travel along different light paths, there can be delays. So, for example, if a supernova goes off in this galaxy, it may appear in 7A before it appears in 7B, before it appears in 7C. You can then use that to constrain cosmological expansion. You can also use this, you can use the spectra, you can obtain spectra of the arcs and get accurate redshifts. So I think that is quite crucial to verify the fact that 7A, 7B, 7C are the same object. The clincher will be to take a spectrum of all 3 of them and the spectrum is identical, the object is at identical, then you can say yes, it's the same object. So all this is happening as we speak, literally, because the JWST has a multi-object spectrograph which can take spectra of many objects at the same time. So you can point JWST at this part of the sky and tell it that, okay, get me spectra of everything I've labeled here. And it will take you a spectrum. Then you can tell. So this is the kind of thing in the bullet cluster. This is the shock. So this, what we've looked at in terms of lensing so far is what's called strong lensing, right? In strong lensing, the shape of the object is completely distorted. But weak lensing also happens, which means the amount of lensing is very small, and so the shape of the galaxy is slightly distorted, but it is not stretched out into an arc or anything. This is very powerful because now you don't have to look. With strong lensing, if you don't see a strong lens, you can't do strong lensing. With weak lensing, you can do it in any direction and on any lens scale. So this is how it works. So suppose you had all spherical galaxies, right, to start with, and then they got lens, right? And depending on, let's say there's a lens here, then some galaxies will get distorted more than others. And if you had all of these galaxies of exactly same shape, then you could actually measure very accurately the mass distribution of the lens by measuring the distortions in the shape of each galaxy. So each galaxy has been labeled with a letter, and the corresponding letter is the distorted shape because of the lens. But in reality, we never have all spherical galaxies. We have a mix of galaxies, right? Some are edge-on, so they look very elliptical. Some are sort of spherical objects like these, and so on. There's a mix. And when this changes to this, it becomes a difficult but not impossible exercise to disentangle the effect of lensing from the intrinsic distribution of the galaxy, of the lensing system. So, suppose you have like these blue galaxies, and let us say they are very far away in the distance. And in the sort of orange and white, you can see the large scale structure. And remember here, lensing doesn't care for baryons versus non-baryons. It's the total matter distribution. So as the light from these blue galaxies passes through the large scale structure to reach us, it bends in various directions, slowly, small amounts. And so the shape of these galaxies as observed by us is a distorted shape. So this is weak lensing in operation, and weak lensing only is statistical in nature. So you can't do it with if you have only one galaxy in the panel. Only if you have many hundreds of galaxies, many thousands. In fact, what is important is the number density of galaxies. Suppose you have few hundred galaxies per square arc minute, like you have with GWST and HST and so on, you can do this very, very well. And then you can build these kind of models. So what they've done, there was a survey called Cosmos, which was done with HST. And in this survey, they had a 2 square degree field of view. Okay, so this into this. But we observed a lot of galaxies at a range of redshifts, which means at a range of distances from us. By doing weak lensing with these galaxies, they were able to map the distribution or the distribution, three-dimensional distribution of dark matter in that direction. And this is what they got. So that those blue blobs are the distribution of dark matter. Clearly, the dark matter is not separate from the galaxies themselves. The galaxies are embedded in the dark matter distribution and or the total matter distribution. But this allows us to map the dark matter observation and allows us to compare with the theoretical prediction directly. Because the main problem in going from the dark matter distribution to the baryonic matter distribution, or using the baryonic distribution as a proxy for the dark matter distribution, is the fact that we don't know exactly how baryons form inside the dark matter halos. So because of that, trying to do this in a sort of baryon independent way is crucial for us to compare the dark matter simulations with the observed universe. Okay. So now a little bit about techniques. You need to measure distances to galaxies. You need to measure their luminosities. We measure the redshift by measuring the shift in the absorption lines of galaxies with respect to their lab measured position. This is easy. Then, knowing the cosmological parameters, we can calculate what is called the luminosity distance. Luminosity distance is that distance such that the luminosity divided by the flux is equal to 4 pi d square. That's your definition of the luminosity distance. So once you have that, once you know the luminosity distance and flux is something you can measure, you can convert that flux into a luminosity. But that's not all. What you want to measure for galaxies, you need to measure their masses, the stellar masses, for example, and their total mass. The total mass we saw you can measure with the rotation curves. How do we estimate the stellar mass? Any ideas? Tell me. Of stars. What is that the formula?
The cube of n.
Cube of n. Is that true for all kinds of stars, but only for low mass stars, high mass stars?
So,
yeah. So there isn't a single formula that allows you to convert the mass, the luminosity of a galaxy to its stellar mass. Okay. So then, how do you do it?
Binary stars and binary. So,
when you use that question, I want to find the total stellar mass of galaxies. See, because remember, stars are not resolved. So you can't, in the Milky Way, you can say, okay, we count the stars, 1, 2, 3, 4, we count. But if you go to distant galaxies, you can't see one star differently from another. You can't count stars.
So we can use mass to light ratio.
Okay.
We can map out the Milky Way and then we can take a average number and then we can
yes.
that with mass.
But will that average number be the same for all galaxies? So it's not that hard. Okay, so you have to find the mass to light ratio of a galaxy. And what are the units of mass to light ratio? It's unitless actually, because it's mass is in terms of solar mass and luminosity is in terms of solar radius. So for galaxies, the mass to light ratio reflects the average mass to light ratio of the entire population. Now it depends on what kind of population you have. Population 1 stars, you've encountered this term. Population 1 stars. No. So these are stars which are predominantly present in the disk. These are the stars that are undergoing star. I mean, they're young stars in the population. if you have a population of young stars, then which stars will dominate the light? It's written there, but tell me why. Yes, the young stars, because they are and also the massive young stars, not just all the young stars. The massive young stars will dominate the light. Okay? Because, as you said, the mass to light ratio for massive stars, young stars, is 3.5, 10 raised to 3.5. So you increase the mass by 10, and the luminosity increases by more than 1,000 times. Okay? So several thousand. So that is why the mass for population 1 stars, the light is dominated by massive stars, and the low mass stars dominate the mass. If you take stars in the bulge of our galaxy or in the stellar halo, there, why do the giants dominate the light? Somebody tell me.
Massive stars are not.
Why are they not there?
They have a shorter life.
Correct. So there are no massive stars in existence in the bulge of our galaxy, because the bulge formed early, and all the stars formed at some early epoch. So the massive stars, which are very short-lived, they're all dead. They have become black holes, or they have become supernova and so on. They're gone. Now what remains are the low mass stars, right? But low mass stars are very low luminosity. They can't dominate the light. But what can dominate the light? The red giants. So the red giants in the bulge will dominate the light. You can ask the question, what is the typical galaxy, and in fact, in solar neighborhood, it has some mass to light ratio. And as you were saying, that you take some average number and calculate the average mass to light ratio, and then you can convert luminosity to mass. In general, mass to light ratio increases with age and luminosity. Correct? You can easily see why it increases with age, right? And metallicity also. Now it turns out that the maximum value of mass to light ratio in any galaxy is 20, and minimum value is 2. So even if you take an extreme value, suppose for a particular galaxy the mass to light ratio is actually 20, but you say no, it's 2. At the other is, your mass estimate will be off by a factor of 10 at worst. At worst. If you take some middle value, you will probably be off by a factor of 5. So within an order of magnitude, getting the stellar mass of a galaxy is absolutely clear. Nothing you have to do. If you want to go better, do better and better than that, then things have to be done in a more sophisticated way. And that way is called stellar population synthesis. It's a very sophisticated technique, but what it essentially does is that it says that, okay, I can think of a galaxy as the sum of light of some number of n stars. Why is that system usually optically thin? Which means, can you have a situation where one star is hiding behind another star? Usually not. Why is that?
Point.
They are point objects. Or another way to put it is, the diameter of a star is negligible compared to the diameter of distance between two stars. Like take the sun. Nearest star is 4 light years. Okay, and the sun is 1 million kilometers in diameter. 1.5 million. So from one end of the sun to the other end, light can travel in 5 seconds. But the nearest star is 4.3 light years. So we use this kind of assumptions, for example, when you read all your ideal gases and so on, right? You assume that the size of the atom, the gas is very small compared to the distance, or the typical distance between the atoms. So there is no shadowing. This is a optically thin system. So if I see a galaxy, I'm essentially seeing all the stars, except for one thing. What is that? Dust. Okay, so dust can obscure. So maybe there are some parts of the galaxy with a lot of dust. I can't see any stars. Okay, or the stars are very faint, so I can't get it. So modulation dust by dust. Modulo the dust, I can measure all the stars. I can add it. Okay, if I take a spectrum of that galaxy, I will get the sum total of the spectra of all the stars. So now this is a very promising technique, because then if I ask the question, what is the star formation history? Okay, how many stars formed at what point in time? And then if I know the stellar evolution process in detail, it means if I know that for a solar mass star, it will stay at this position on the main sequence for so many billion years. After that, it will move within this time to the red giant phase. After so many years, it will move to the white dwarf phase. Suppose I know all of stellar evolution, which I do. Then, if I know when the stars formed, I can do arithmetic projections on. It's like projecting what will be the population of India 20 years from now. You have to know the birth rate, you have to know the death rate, you have to know how the birth rate is going to change with time, how the death rate is going to change with time. If you know all of these parameters, it's easy to predict the population 20 years from now. So that is it. Is there anything else? You also need to know the spectrum of a star at its particular stage of its evolution. So if the sun is on the main sequence like it's now, it's going to have a very different spectrum from the red giant. So when it is a red giant, its spectrum will change. So you have to keep track of that also. Okay, sun has become red giant now. So now if I want take its spectrum, I shouldn't take its regular spectrum, I have to take the red giant spectrum. So if you know this motion of all stars on the HR diagram as a function of time, and you know the spectra of all stars as they move along their tracks, then it becomes a matter of arithmetic. Modulo the dust, of course, becomes a matter of arithmetic to calculate the entire star formation history of the galaxy by measuring its spectrum or by measuring its even its broadband fluxes. You don't even have to measure, get a high resolution spectrum. A low resolution flux measurement can also do it.
How do you know the initial? You said you also need to know the initial. How much was the
Initial meaning? What you need to know
you
is
said
the
right,
star.
if you know the initial, how many stars are over there, you can just add it and you
Yes. So you need to know star formation history. Okay. So what you need to know is you need to know the psi of t as a function of time. The psi of t is of course a function of time. How many stars were formed every year for Milky Way over the last 10 billion years?
Aren't we trying to find that?
You are trying to find that because it's an inverse problem. Because what you're trying to do, you're trying to determine the star formation history of it. What you have is the sort of integral. So what you do is, since there are some degeneracies also. There can be situations where there are multiple star formation histories that fit the data. Then you have to break that data, perhaps by measuring metallicity. Because metallicity, chemical evolution of the galaxies also happens. So what you can do is, okay, if this is the star formation history, the metallicity should be 0.5. If this other one is the star formation history, metallicity should be 0.5. If that much difference is there, you go and measure the metallicity, you break the data.
You're just backtracking and seeing which parameters.
And what you actually do is the parameter space is so large that you don't try to do it like a minimization problem, chi-square minimization problem. What you do is that you build all possible brute force, you build all possible star formation space, right? And perhaps you do it in a crude way first. You build the star formation trees assuming a simple possibility, star formation after 1 gigayear, after 2 gigayear, after 4 gigayear, etc. Then you refine it that okay, this thing looks like it had star formation somewhere between 3 and 4 billion years ago. Then I build a whole family of models which are centered on that range. And say that okay, now is it 3 billion, 3.1 billion, or 3.2? You do one. Very, very sophisticated part of stuff. So now a little bit about supermassive black holes at the centers of galaxies. I won't talk much about it because this is something that will be discussed. AGN will be talked about quite a lot in lectures to come. Okay, so this is M87. It's an elliptical in the Virgo cluster. So some years ago, with a telescope known as the Event Horizon Telescope, astronomers went and measured, took a photograph of that black hole which is sitting at the center. And the solar system is given for scale over here. So this is a very massive galaxy. It has a very massive black hole, 5 billion solar masses. How will you calculate the supermassive black hole mass from an image like this?
Yes, assume that the dark region is the size of the black hole and then just convert the radius.
Yeah, so you can assume the Schwarzschild radius is what you see. Actually, this image is quite.
இங்க குட்டிடா இது அப்படி இதை முன்னாடியே குத்துனா அவ்வளவு கஷ்டப்படாம நான் பண்ணிருக்கேன்.
Please mute. Anyway, so this gravitational bending of light due to GR effects that causes a lot of distortion in the image. So this really is not. Then even light from behind can sort of curve around and come towards you. So it requires a lot of modeling to get right, but it's doable and people have done it. And they can therefore calculate exactly what should be the radius of the Schwarzschild radius. Yeah.
So just wanted to point out that this might also be a naked singularity. Is what they said after releasing this image.
Okay. So if you know the Schwarzschild radius, which is the formula for the Schwarzschild radius, you can simply plug it in and get the mass. So the Milky Way's black hole mass has also been measured using two techniques. Okay, one is this kind of technique, the Event Horizon Telescope, but even more clever technique, which was for which the Nobel Prize was awarded a few years ago. So what you can do is you can, using adaptive optics, you can actually see how the stars near the black hole at the center of the Milky Way move. And this is projections into the future. Okay? So we'll be able to track the elliptical motions of stars close to the black hole. Black hole is somewhere there, and therefore, as stars come closer to the black hole, uh, they go faster. And again, you will use the virial theorem, or you use just the fact that the centripetal acceleration is being provided by gravity to calculate the mass of the black hole. And how do you measure SMBH mass of external galaxies? There you can't see individual stars; they're too far away. So there you can use the velocity dispersion. So what is shown here is the value of the velocity dispersion in kilometers per second as a function of radius. And the velocity dispersion turns out to be quite high near the center, and you can use that peak velocity dispersion value to calculate the mass of the black hole. Very interesting correlation has been observed. The mass of the black hole, log of that, is correlated with the luminosity of the bulge, and therefore mass of the bulge also. Have been measured for many galaxies. There is reasonable scatter, but there is a clear trend. So, what does this indicate? This indicates that the properties of the very center of the galaxy seem to influence properties of the galaxy on much larger scales, kiloparsec scale. This also means that very likely the growth of the bulge and the growth of the black hole occurred at the same time and for the same reasons. And therefore, this correlation emerges. The study of AGN is started in earnest in 1963 with the discovery of PC273, the very nearby quasar by Martin Schmidt of Caltech. And these quasars were special because they were star-like in optical, they were very high redshift, were luminous in wavebands. They were variable on time scales of several hours to days. And could these be powered by nuclear fusion? Not really, because people did the calculations and showed that the amount of energy that had to be concentrated, a very small volume, very unrealistic that this was being done by nuclear fusion stars. And therefore, the alternative explanation emerged, which is the popular explanation today, is that these quasars or all AGN are powered by gravitational contraction. So things are falling in, losing potential energy, and that potential energy is getting converted into heat and light and outflows and everything. You'll learn about this in the lectures by Yogesh on AGN. But I just wanted to show this as my last slide because just to bring home the fact how special AGN are. So this is a typical CD galaxy. M87 Virgo is a CD galaxy. And look at it's a pretty massive CD galaxy, but it barely emits any radiation compared to this. So this is the luminosity of PC273. SED stands for spectral energy distribution. Compared to a massive elliptical, it's just bright everywhere. All the way from the lowest frequencies to the gamma rays. So we'll stop here and I'll spend the next 10 minutes taking any questions. There's something on the chat.
Do we know what kind of objects quasars are?
Yeah, we know. You learn about them, and I don't want to steal the thunder of the next speaker. But these are basically objects where things are falling onto the black hole. And as it's falling in, it's either producing a lot of hot material, hot plasma around the black hole, which is leading to emission of these X-rays, gamma rays, etc. Or in some cases, it's forming jets of outflowing materials that reaches very high speeds and travels very large distances. So those give rise to radio jets and radio loads.
How do you measure the mechanism of the entire galaxy?
How do you measure the metallicity of the entire galaxy? You take the spectrum, and metallicity can be defined in terms of the strengths of certain light ratios. So you measure the effective, you'll have to take a spectrum of the whole galaxy, not just of its center. Nowadays, there are what are called integral field spectrographs that allow you to take a spectrum of the whole galaxy. And then you use those observed line ratios to calculate the metallicity of the galaxy as a whole. This is exactly the same as what you do for a star. You take the spectrum of the star, except for here there are complications. That in a galaxy, you have the concept of a gas phase metallicity and stellar metallicity. So there are certain lines which arise in stars. So those will give you the stellar metallicity, those line ratios. There are certain other lines like H alpha, H beta, etc., which arise in the gas. So their ratio will be the metallicity of the gas.
You were saying that you were talking about how to measure the stellar mass of the galaxy. How do people measure the mass of the gas component? Is it possible?
Measuring the mass is much more difficult than measuring the stellar mass. Okay? Because there's no prescriptive formula. So what has been done so far is that with the large amount of optical data that we have, we can measure quite easily the amount of ionized gas, that is, using the H alpha line or the other Balmer and Galaxies lines. But to measure the amount of neutral gas and the amount of molecular gas has proven to be quite difficult. With the radio also, you can detect H1 in emission only to short distances. So we don't know. We have H alpha based ionized gas measurements of hundreds of thousands of galaxies, if not millions. But if you ask how many galaxies do we have H1 measurements by studying their emission, it's like a few hundred. And molecular gas also similar. You require the very sensitive telescope like ARMA to measure the carbon dioxide levels and use that to calculate the You can't do it. Technology. Anyone online who wants to ask, you can please. You can raise your hand.
I had one last question.
Yes.
It was 2 slides earlier when you were showing the correlation.
Yes.
Yeah. So you were saying that since they are correlated, they might have influenced each other. Is there like if you plot mass of galaxy instead, is it still a straight line?
No, it's not, because it correlates only with the mass of the bunch.
It's not true that the galaxy is heavier, the supermassive black hole is also there.
It's true, but the scatter is much larger. So, for example, there are galaxies that have virtually no bunch. So, by this formula, they shouldn't have a black hole. And there are now upper limits. So, for example, that third galaxy in our local group, M33, that has virtually no bulge. And people have tried to measure using the velocity dispersion at the center of M33, tried to measure the black hole mass. And they don't have measurement, but they have an upper limit, which is 1500 solar masses. It's less than 1500 solar masses, which is quite tiny compared to our Milky Way, which is about 5 million solar masses.
So it's true that
This does not correlate well with the total mass of the galaxy. It correlates well with the bulge mass of the galaxy.
Seema, you can unmute yourself and ask question.
Yeah.
There is a question from Seema Yogesh.
Yes.
Hello, sir. Am I audible?
Yes, you are audible.
Yeah, sir, there's just one basic confusion I'm having. Like, we say that sun is exhausting, so sun mass is getting lower and lower. So we say the universe is expanding, right?
Yes.
Yeah. So universe is expanding. At the other end, we say the black hole, all the masses are collapsing, and as you say, we are having the emission of radiations also from the black hole. So is the two things doing the same, like in universe expansion?
I'm not quite understanding your question. What?
The first thing is sun. We say that sun will exhaust after several years, right?
Yes, several billion years.
Yeah, several billion years, right? So that is a one cause for the universe expansion.
No. That has nothing to do with the universe expansion. No.
But universe is expanding, right? The redshift gives the universe expansion.
Yes.
So universe is expanding, and the my confusion is there. Universe is expanding, and we are having the galaxies. We are having the black holes. The black holes are attracting. The masses are going there at the center at the black hole. But then, so
even if the mass falls into the black hole, the mass doesn't disappear. I mean, it doesn't emit light anymore, but it contributes to increasing the mass of the black hole. So
yes.
It's not that the mass has disappeared. It's there.
Okay.
That's the idea. And so it's not as if the black hole, and also it's not a contradiction that the regions around the black hole are emitting.
Okay.
Remember, outside the Schwarzschild radius, the light can escape. No problem. So the light that we see is not coming from inside the Schwarzschild radius. It is coming from outside the Schwarzschild.
Okay, sir. Thank you.
Yeah. Any other question online or here? Yeah. Yes.
Does that mean that the star formation regions are like concentrated in the center?
Usually star formation, it depends on whether it is what kind of galaxy it is. If it is a disk, spiral galaxy, then the star formation is quite well distributed around the disk. But if you have a very compact spheroidal galaxy, then the star formation can be quite concentrated near the center also. And remember, the star formation is a very, very sensitive indicator. Anything goes wrong, the star formation properties change very rapidly. You go in environment changes, that affects star formation. Merger happens, that affects the star formation. Something pulls out the gas from the galaxy, that affects star formation. So star formation can be lowered or increased by a variety of factors. And then here, was there any questions?
Yeah. Is it in the slide M by L? You said it increases with age and metallicity.
Yes.
Age seems like it's a bit intuitive, but is it intuitive by if metallicity increases, M by R will increase.
Mass to light ratio increases with age and metallicity. So, if you have low metallicity system, the lower the metallicity, the more transparent is the outer atmosphere of the star. So that leads to, for a given mass, etc., it leads to a higher luminance. If you have two stars, one is one solar mass star, other is one solar mass star. Okay, they're both on the main sequence. But this fellow has a higher luminosity and this fellow has a lower luminosity. The lower luminosity guy will be brighter.
Lower luminosity.
No, sorry. What did I say?
Higher metallicity.
The lower metallicity guy will be brighter, will be more luminous. And because of that, the mass to light ratio increases. So the higher metallicity guy will have a higher mass for the same luminosity. Or at the same mass, it will have a lower. I don't see any raise hands amongst the participants. Okay, if there are no further questions here, we will stop. And this is I'm giving only 2 lectures. So I apologize for the fact that I've tried to cover a few topics from a very large field. Okay, Galaxies is a very, very vast field of research. And therefore, in the first lecture itself, I pointed you to a 21 lecture course that I gave last year. Want to learn about the details, please listen to the videos. They're on YouTube. Stop sharing. Stop. I think you have a break, right? Before the next.